In this particular lecture, we'll take at some of the important tenets from linear algebra, because in the lectures on statistical properties of H, we use some of the important results from linear algebra, as well as when we go down further, we'll be again using linear algebra a lot. So essentially, one can consider linear algebra as one of the prerequisites. So for MIMO communication, that's natural for anywhere you take any subject on this particular topic. What we do is we summarize some of the important tenets of linear algebra so that it's useful for you. Using these, you can always refer back to some important text. I can give you one important author who has been contributing a lot, and the book is quite easy to read. This does not necessarily mean that this is the only book available. There are many others, up to your own choice, but a book by Gilbert Strang is quite useful. There are many other books also in the market, but that's quite easy to follow. So we get started with our job in the linear algebra, and let us consider a vector. So we'll be dealing with vectors. We'll be representing vectors with an underline, a single underline. So this appears to be multiple lines, so this will be a single underline. That's a vector. Let's consider it has two elements, v1 and v2, right? So this is the basic representation of a vector, and you can have a scalar multiplication, c times v. If c is a scalar, it results in c times v1 and c times v2. That means the components. So typically in two-dimensional space, you're well aware of if these are the two axes, there's a point, component on one, component at the other. So this I would write v1 comma v2 as this point, or you could denote it by the vector v1 v2. That means these are the two components on the two directions. And a scalar multiplication means it simply scales to a certain size. This one scales, it scales also in that direction. And of course, we have to remember that minus v plus v is not equal to the number 0. It's not equal to the number 0, but it is equal to the 0 vector, which means it is 0, 0. Right? That is very important. That means we are talking about the 0, 0 point. It is not equal to simply a 0. Okay, the components on each of the directions are 0. If we take the dot product of v with w is equal to, both contains v1, v2 as the two elements, and w1, w2 are the two elements. It is v1 w1 plus v2 w2. That is what you get. And if v and w are orthogonal, you're going to get the answer as if v and v is orthogonal to w. Is orthogonal to w. Orthogonal means I'm indicating it at 90 degrees. The dot product is 0, because what we are doing here is, if this is one vector and this is another vector, we are basically, dot product means taking the projection of this on this vector. So that's basically projection of one on the another. And once you take the projection, if this is at 90 degrees, suppose this is at 90 degrees, in that case the projection of this will be at the point 0. So the result is you don't get any component on the projection, so it is 0. If you take v times v, that means a vector of v dot v, this is basically the length squared, or it is indicated as v norm squared, and or you could also write as the length of a vector, v could be given as square root of the dot product with itself, which could also be written as sum over vi squared. So basically v1 squared plus v2 squared, square root of that is the length of the vector. And you also have another thing called the unit vector. The unit vector is a vector of length 1. It has a length 1, and the unit vector for v could be defined as v divided by the length of the vector, right? This is the squared length, so this is the length. Length means square root of this. So that is how you would do it. And if you have two vectors v, two unit vectors, let's say v and u, and I take the dot product of it, what you're going to get is cos theta. So again, this is going to tell you, because they are length of 1, and so this basically gives the angle between them. So basically this lies between plus and minus 1, and if they are at 90 degrees, the cos theta is basically cos of 90, which is 0. So that is also again shown by this particular result. So mod of v dot u is less than or equal to 1, or v dot u lies in the range of minus 1 to plus 1. And with this we proceed on to write the Cauchy-Schwarz inequality, which will be used elsewhere also, as v dot w is less than or equal to the length of v times the length of w. So this is used in results on matched filter and other places. Moving forward, if we have linear equations, let's say x plus 2y plus 3z is equal to 6. Suppose this is one linear equation. We have 2x plus 5y plus 2z equals to 4, and let's say 6x minus 3y plus z is equal to 2. In this set of linear equations could be written down in the matrix form as 1, which comes from here, 2, which comes from here, and 3, which comes from here. Then 2, 5, 2, 2, 5, 2, 6 minus 3, 1, 6 minus 3, 1, and here it is x, y, z. So what you have, x, if you do this product, 1 times x plus 2 times y, 1x plus 2y plus 3z is equal to 6. 2x plus 5y plus 2z is equal to 4. You can read 2x plus 5y plus 2z. Finally, 6x minus 3y plus z is equal to 2. So if we write this as a matrix equation, we could write this as A times let's say sum capital X is equal to, let's say, B. So this is the vector B, this is the vector X, this is the matrix A. So if you solve this, then you can find the values of X, Y, and Z. This could also be viewed as if we are writing 1, 2, 6 as one vector times a coefficient plus 2, 5, minus 3 times y plus 3, 2, 1 times z is equal to 6, 4, and 2. You could also view it in this way. That means we are talking about some combinations of vectors which is going to produce this particular vector. So this is one vector, one vector, one vector, which is getting multiplied by some components, some weights, so that it produces this vector. So you could also view it in this form. In this context, the I matrix is basically 1, 0, 0, 0, 1, 0, 0, 0, 1. This is a 3 cross 3 I matrix. In would be 1, 0, 0 up to n, 0, 1, 0, 0, 0, 0, 1. This goes on up to n. So it's only diagonals of 1, and definitely we have I times x is equal to x. This is a very important result. So basically you can clearly see 0, 1, 0, 0, 0, 1 times x1, x2, x3. What would you get? X1, if you look at the second row, 0 times x1, 1 times x2, 0 times x3, x2, 0 times x1, 0 times x2, 1 times x3, x3. So basically Ix is equal to x. This is again a standard result. We move further to look at symmetric matrices. So when we talk about symmetric matrices, those are those matrices, if you take the transpose of them, they are the matrix itself. So basically if I write 1, 2, 3 and I take a transpose of this, it's basically 1, 2, and 3. So that means there is a certain diagonal and these components are same, right? So if we have it like that, it's a matrix. So basically I can write A11, A12, A13, and I would also have this component A12, A22, A23, and again I should have A13. So basically A31 is the same as A13. I have A23 is A32 is the same as A23, A33. So this is a symmetric matrix, because if I transpose this, this row becomes this column, and this row becomes this column, this row becomes this column. So if you transpose this, it is the same as itself. that's a symmetric matrix. So that is very, very useful, and we often come across them, especially when we are taking H Hermitian. Of course, this Hermitian symmetric, that's one level higher than this. If we take A transpose A, that means we are taking symmetric matrices. If A is a symmetric matrix, it could be decomposed into L du, where L is a lower triangular matrix, D is the diagonal matrix. Diagonal matrix means it has only D1, D2 elements in the diagonal, rest of them are or 0. Diagonal matrices are very, very useful. This is an upper triangular matrix. These diagonal entries are very, very useful in the sense that you have very simple multiplication to perform. Even lower triangular, upper triangular matrices are very, very useful because you can solve the solution of this in iterative steps. If it is diagonal, you get direct solutions. Next, we move to inverse of a matrix. It is represented by A inverse. Inverse would, if an inverse exists, then we would have A inverse A is equal to I. That means if I multiply the inverse with the matrix, I am going to get an identity matrix. That's the fundamental definition of what an inverse should be if it exists at all. And you could also say that if I have A inverse times AX, basically if I am looking at the solution of an equation, I am going to get A inverse of B. So what I am writing over here is what I wrote here. If I look at this particular expression, what I wrote there, if I would write, I multiply A inverse on both the sides times X, A inverse times B is whatever I have written over here. So what do I get? A inverse A is I of X is equal to A inverse B, and we have also said that Ix is equal to X. That means I times X is X. So basically X is equal to A inverse B. So if the inverse exists, we have the solution to the set of equations as X equals to A inverse B, and if the inverse exists, this is a unique solution to this particular problem as described by this set of equations. So inverse is very, very useful. So if inverse exists, we can use it to solve a particular set of linear equations. If a matrix is invertible, of course we have said that A inverse A is equal to I, and A inverse is also equal to the identity matrix, and the truth is there is only one inverse. It is unique. You don't have two different inverse for the same matrix, and therefore when I do X equals to A inverse B, I get a single unique solution for the same. So that's very true. And now suppose I take this equation that Ax equals to 0 instead of Ax equals to B. So this is a very, very particular case that I have A as a matrix. Just try to understand this. If we have A as a matrix, all these entries are 0, x1, x2, x3, right? I have a certain matrix over here. So in this case, if X is non-zero, one possible way of getting it 0 is I put X as 0, because this is A11, A12, A13, A21, A22, A23, A31, A32, A33. So look at this equation. It is A11 times x1, A22 times x2, A13 times x3. So this row A11 times x1 plus A12 times x2 plus A13 times x3 is equal to 0 as per the first row. Now this will be 0 if x1, x2, x3 are 0. So if they are 0, this will be 0. So all of them will be 0. Now we are saying that suppose x1, x2, x3 are non-zero. If they are non-zero, yet it is going to 0. That means there is a certain combination of x1, x2, x3 such that this whole product is going to 0. Same with the other products. Then this vector x is known as the null space of A, and all such solutions, this could be x vector 1, there could be x another vector, that means another combination of x which could lead to 0. So all these from the null space of A. That means when it is multiplied with this matrix, they turn to be 0, right? And why it is called as the null space, and what is important to remember is that I cannot get back x if I am going to take the inverse from this, because just imagine that I multiply A inverse, suppose I multiply A inverse, right, what do I have? I have x equals to something multiplied by 0. So I cannot really get back to x even if I have something over here. So no matrix can bring back x from 0. This is very important to understand, and this is called the null space, because whatever is the matrix, it is going into 0. We cannot recover x once we have got to the 0 state. So this is one of the important matrices that will be used. If we have a diagonal matrix, if you have a diagonal matrix, so diagonal matrix is like d1 0 0 0 d2 and dot 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 dot. The A inverse is easily found by 1 by d1, 1 by d2, 1 by dn. Rest of them are all zeros, right? This is very useful. So if I have a diagonal matrix, finding inverse is very easy. So that's why I would like to have diagonal matrices. If I have A inverse, I take the transpose of it, I could write it as A transpose inverse. Now if A is symmetric, if A is equal to A transpose or A transpose is equal to A, I could write this as A inverse. So that means that the inverse of symmetric matrix is also the inverse of a symmetric matrix is also symmetric. That's what we can see. See, A inverse transpose is equal to A inverse. So if let's say A inverse is equal to B, so what we have is B transpose is equal to B, right? So I've taken A inverse as B, this is B, B transpose is equal to B. So that means if A is a symmetric matrix, the inverse is also symmetric. So that is also very useful. So whenever we have symmetric matrix, it is very useful. For rectangular matrix R, if R is a rectangular matrix, then we have, let's say, RT times R transpose times R. This is a square matrix and this is a symmetric matrix, is a symmetric, right? Because it is clear RT times R. If I take the transpose of it, what do I get? R transpose times R transpose times R transpose. R transpose is basically R. So what you have, RT times R whole transpose is equal to RT times R. So basically that is a symmetric matrix, not a problem. We have the subspace concept. So subspace of a vector space, if we talk about subspace of a vector space, is a set of vectors, including the 0 vector, right? So it's basically contains two tenets. The first tenet is the sum of two vectors is in the subspace, and the second tenet is some scalar times the vector is in the subspace. Essentially we can say a linear combination of these two vectors is in the subspace. So a combination of this remains in the subspace, so that's a vector subspace. So if C is 0 and D is 0, then this would turn out to be 0. So including the 0 vector is the subspace. So if 0 is not contained in it, it is not a subspace. Then there are many other spaces, the column space, the row space, and so on and so forth. We'll not look into that. We'll go into determinant, which we use. So determinant is one of the very important things. So if we have a square matrix, so for a square matrix, determinant is a single number. This is very important. Determinant is not a matrix, it's a single number. It tells us whether it is invertible or not. If the determinant is equal to 0, it implies the matrix is non-invertible, and if it is if it is not equal to 0, it means it is invertible. So if you calculate the determinant and find that determinant does not exist or determinant is 0, you will never be able to invert the matrix, because the determinant is the adjoint of the matrix divided by the determinant. So this is very important. If you have pivots, then the product of the pivots gives the determinant. This is also important, and other easy way to remember that if the edges of a box are the rows of a matrix, right. So, the edges are the rows, then the volume is given by the determinant of A. So, determinant of A could also be written as two straight lines around A or as det A. So, these are the two ways of writing determinant. So, once we have studied determinant, we can go on, and what we can see is that there are something called the eigenvalues. These are very, very important. Eigenvalues is very special value in such a way that we'll come back to determinants again, that if I have a matrix A and I multiply this with the vector which is known as the eigenvector, I get the vector back itself along with the eigenvalue. So, this eigenvalue tells us that by this operation of this matrix, whether this vector has become something which is similar to the vector, something in the sense whether it has become whether it has remained the same. So, if it is equal to 1, there is no change. If it is positive, that means it has grown, positive and greater than 1. If it is between 0 and 1, then it has shrunk, right. If it is negative, that means it has changed direction. So, what it means basically the set of and these vectors, these x's are known as eigenvectors. So, basically for a given matrix, if we multiply with a certain vector, the vector remains unchanged. That means this matrix operation of the vector remains unchanged, and there is a special value along with that. So, these are eigenvectors, and along with that we get eigenvalues. These are very special values, such that when the matrix operates on the eigenvector, the vector remains as it is with certain scalar coefficient. The scalar coefficient is going to tell us what has happened to that vector. If it is 1, nothing has happened to the vector. If it is negative, the direction has changed. If it is something which is 0 and 1, it has become smaller than the original vector, and so on and so forth. So, once we have these eigenvalues, they can be found by solving a determinant of A minus lambda I. So, if you solve this determinant of A minus lambda I equals to 0, you are going to get the eigenvalues of it. Once you get the eigenvalues of it, then you can solve for eigenvectors. These eigenvalues are very important, because if you are multiplying the eigenvalues, the product of eigenvalues will give you the determinant of the matrix A. So, that is why the product of eigenvalues are very important. And the other important thing about determinant is, if we have t times A times t times B and C D, that means I am multiplying one row by a certain t, this and taking the determinant, this is equal to t times the determinant of A, B, C, D. So, if I multiply a matrix with t, in that case all the elements gets multiplied, all the row gets multiplied. The determinant is the determinant of the original matrix multiplied by t to the power of n. So, let us say determinant of 2I is equal to determinant of 2002, because 2 times I is 2 times 1001, right. So, which is equal to 2002, and these lines indicate the determinant, which is equal to 2 squared times determinant of 0110, which is equal to 4, because determinant is this minus the product of this. So, determinant is also very important. We should try to understand determinants. The last thing about determinants, I would say determinant of A transpose is equal to determinant of A, and the determinant is 0. The determinant of A is 0 if there are dependent rows or dependent columns in this, and if there are 0 rows, then also the determinant is 0. So, these are some of the important cases that we have. So, moving forward, when we look at these eigenvalues, as we were seeing, so we have said that eigenvalues are very important. We have seen them. So, if I solve A minus lambda I times mod determinant of that equals to 0, that means A is the matrix which is given, I matrix is known, lambda has to be found. So you can solve this equation and you can find the lambdas, right. So if you take A as A11, A12, A21, A22, let's say this is the matrix, minus lambda times 1 0 0 1, and take the determinant of that, set equals to 0, you're going to get the solution of lambda. So basically what you have here is equal to A11 minus lambda, and A12, A21, and A22 minus lambda. So basically A11 minus lambda, A12, A21, A22 minus lambda. So you take the determinant of this, set it equals to 0, so you're going to get quadratic term. There are two lambdas, lambda 1 and lambda 2. So once I have got this, then I can put Ax is equal to lambda x. I know this, I will put the two different lambda values one at a time. I am going to get two different vectors x1 and x2. In this way, I am going to get the eigenvectors as well as the eigenvalues related to A, which will be very, very useful in our future description. So eigenvectors are again useful for factorizing A in terms of its diagonals, and when you are able to factorize it in terms of diagonals, you can really do a lot of things. You can calculate the determinant easily, you can do the inversion, and so on and so forth. So yeah, so these are some of the important things. So now suppose we have this matrix A, right, and we can diagonalize it in the form that I would put S inverse S is equal to lambda as the eigenvalue matrix. I could diagonalize it as eigenvalue matrix, where these S would be containing the eigenvectors of A, and in that case we could write A is equal to S lambda S inverse. So if I have it in this form, then I could this could be very, very useful. This would be really very, very useful. And the important thing we should remember at this point is lambda i's, they will all be different. So if these lambda i's are different, that means when we are solving this particular equation, getting the lambda 1 and lambda 2 to be different, in that case this x1 and x2 will also be independent. In that case x1 and x2 would be independent. So if lambda i's be different, then you will be getting x1, x2 up to all the eigenvectors are independent. And if they are independent, then you again have a lot of useful values. So if all of the lambda i's are not equal to 0, the matrix A is invertible, in the sense that determinant is equal to product of all lambda i's. Okay. So if they are non-zero, I am going to get it invertible. If any one of them is 0, the determinant is 0, that means it is not invertible. And diagonalizability means if all lambda i's are different, if they are different, you can diagonalize it. This is an important result. So if we have to diagonalize this, then I need all of the lambda i's to be different. If you have a symmetric matrix is what we have seen. In that case, that means when A is equal to A transpose, if you have A is equal to A transpose, you can get S, that means what we have over here, S inverse is equal to S transpose, and S definitely, if S inverse is equal to S transpose S is equal to I, because S transpose is S inverse. So basically S inverse S, which is equal to I. This is a well known result. So this holds true. And for a symmetric matrix, means if it is symmetric, then the eigenvalues, then lambda i's are real. This is again another useful outcome. And for such cases, you could also choose these eigenvectors to be orthonormal. So if eigenvectors are orthonormal, so S lambda S could be written as Q lambda Q transpose. So eigenvectors, if they are independent, they are orthogonal, and in this case you could make it orthonormal, because that means you are going to have them as unit length. That's the only difference that you are going to get. And the next important result we are going to have is if all lambda i's are greater than 0, then what you have is a positive definite matrix. If they are all greater than or equal to 0, it is a positive semi definite matrix. Right. So these are the two important terms which we'll be using. Symmetric matrices will be getting quite often. The last thing that I need to mention before we close this particular session is singular value decomposition. Singular value decomposition. So as we have said that you could write a x is equal to lambda x. That means these are eigenvectors. This is an eigenvalue of the matrix X. Consider sigma i's as the singular values of A. So if these are singular values of A, you could write matrix A times V is equal to some vector, singular vector sigma 1 times the vector u1. So these are the input singular vectors and the output singular vectors of the matrix, and these are the singular values. So like this, you can to have r number of singular values, where r is the rank of the matrix. Rank of the matrix for a square matrix would be the number of independent rows or columns, or otherwise it's a minimum of rows and columns. So this is almost similar to this eigenvalue decomposition. In this case, you could factorize A as, like in the earlier case we had S was used to diagonalize this. That means we had S lambda S inverse was the diagonalization that we had used. Basically we had said that AS is equal to S times the eigenvalues. I would multiply the S inverse on this side, and I'm going to get, so in this expression if you multiply S inverse, you're going to get S lambda S inverse, which is this particular expression. So here, using this, you could write it as AV is equal to U times sigma. These are all matrices, and in other words, you could write A is equal to U sigma V Hermitian. If I'm going to multiply by V Hermitian, I'm going to get an identity matrix, because V transpose V is equal to I and U transpose U is equal to I. These are true. So I'm writing Hermitian for complex elements. So we could again diagonalize A with orthogonal matrices in U and V, and this containing the singular values of A, just like we have been able to diagonalize using the eigenvalues for A. So these are some of the results which we'll be using in the study of MIMO communication systems. And for example, when you study the statistical properties of H, we have used most of the results for this. Again, I would like to say that this is a very brief introduction or summary of results for from linear algebra. I would strongly recommend one to have a reference book on linear algebra whenever you are doing such a course. Thank you.